I'm Boyuan He, a PhD student from Zhejiang University, China. And today, it is a great honor for me here to present our work, SSLINT, a tool we implemented to automatically verify SSL API usage in applications by static analysis and report vulnerabilities whenever this verification fails. This work is conducted with the joint lab of Internet and Security Technology at Zhejiang University and Northwest University, supervised by my advisor Yan Chen, and also collaborated with our alumni Yinzhi Cao from Columbia University and Professor Venkat Krishnan from University of Illinois at Chicago. And as we know, SSL and TLS protocol have become the security backbones of Internet today. As a transport layer protocol, SSL usually uses TCP as underlying protocol, and many application layer protocols are built on top of it. And the SSL provide an end-to-end encrypted communication security over the Internet. As a result, many software, including mobile, excuse me, and desktop applications are protected by SSL protocols. And SSL is based on the model of public key infrastructure and X509 certificate, and is designed to guarantee the confidentiality, authenticity, and integrity for communication against the man-in-the-middle attacks. However, recent studies show that some SSL applications are still vulnerable to man-in-the-middle attacks because of implementation flaws. In many cases, SSL library APIs are not well designed, so the developers fail to understand them correctly, and they also fail to use them correctly. So previous work has already mentioned that this incorrect usage problem, especially in the server certificate validation on the client side, showing that many applications are affected by this problem and making all of them vulnerable to man-in-the-middle attack. So motivated by this SSL API usage vulnerabilities, we wonder that since SSL is so important and widely used, how many such unknown vulnerabilities are still there, and whether it is possible to automatically detect such SSL vulnerabilities in a large scale and in a more general way with the high efficiency and accuracy. To answer this question, we propose an approach as well as a tool called SSLINT, a scalable static analysis framework which is aimed to automatically identifying incorrect usage of SSL APIs in the client-side applications. So our work has four main contributions, and the number one is we design a systematic approach to automatically detect incorrect SSL API usage vulnerabilities. And the second one, we implemented an SSLINT, a scalable automated tool to verify SSL usage in applications. The third one, in order to find all the applications using SSL library APIs as our candidates, we're leveraging on the existing package managers, which existing in many Linux distributions for automatically compilation and analysis, and then acquire all the target applications with SSL library as their building dependencies. In the end, we did a large-scale measurement and analyzed more than 22 million lines of code and discovered 27 previous unknown SSL vulnerabilities in the software packages from the Ubuntu 12.04, and we confirmed all of them, and so far four have been fixed. Sorry. Here comes the agenda for the rest of my presentation today. We start from some background knowledge of SSL vulnerabilities and show how man-in-the-middle attack can happen, and man-in-the-middle can happen due to the incorrect API usage. Then we present our SSLINT design and implementation, including code representation we use in the static analysis and signature design. At the end of the presentation, we give a summary of our findings. We start from some background knowledge showing how SSL protocol works. And as a transport layer protocol, SSL is built on top of TCP. So after a successful three-way TCP handshake, and the SSL handshake is established from the client side, and then the server presents the certificate for the client to verify, And this is authentication phase for the SSL, and usually the client certificate is optional according to the RFCs. So in fact, the one-way authentication is a common practice in many SSL applications, as shown in this example. And after a successful authentication, the keys and ciphers will be exchanged between the client and server before the handshake is done. And in the end, a secure communication channel is established, and encrypted application data can be transferred over this channel. As mentioned earlier, SSL is designed to secure an end-to-end channel between the client and server to avoid man-in-the-middle attacks. However, it may still be possible, it may still be vulnerable to such attacks if SSL protocols are not implemented correctly. Incorrect usage of SSL APIs make it possible for attackers to bypass certificate validation, and in this way, attackers can easily intercept, decrypt, or tamper all the information inside the SSL channel. In other words, the SSL is completely broken under such attacks. So we will present a demo video of such attacks against the one vulnerable email app we found at the end of the presentation. In order to show the details of these vulnerabilities and the idea of our system design, now we present a motivating example from a real vulnerable app we found. This application uses OpenSSL as its SSL implementation, and the first API, SSL CTX new, as you can see in the first line, is called to create an SSL context, which is for SSL configuration. And then the second one, the SSL new, is called to create an SSL session using this context. For next, SSL handshake is launched using the SSL connect API. After all this is successful establishment of the connection, another API, SSL get verify result, is called here to see if the certificate validation is successful and terminate the connection if necessary. This is one of the common practice or correct usage when developing an app using the OpenSSL library, and we refer it as checking after handshake. However, OpenSSL API is not well designed, as most of you may know, and well documented. So the SSL get verify result function will still return a successful flag if no certificate is presented by the server. So in this way, this app is vulnerable. To fix this vulnerable app, another API, SSL get peer certificate, should be called when checking certificate validation results. So in this way, the app will terminate the connection when no certificate is presented by the server. So in order to automatically detect such SSL vulnerabilities, including those shown in the motivating examples, we first model the correct usage of the API, SSL API as signatures. Then we design SSLINT, which takes the source of the app as input, and then transform the source code into a certain kind of code representation in a static analyzer, and then match the signatures to detect the vulnerabilities. Remember that it is the correct logic that we model. So in the signature, so the vulnerabilities will only be reported whenever the signature match fails. In order to show the ideas of the signature design, here again, we use our motivating examples. This is a fixed version representing the correct logic of the OpenSSL APIs when validating the certificate. To model this correct logic, first, our signature needs to track the data flow between all of these APIs. So starting from the SSL CTX new, as you can see at the line 1 on the left, here are all the data flows we need to track, including all the SSL, critical SSL APIs. And also, there are some if conditions in this data flow. In addition to this data flow, the control flows related to the SSL API's usage also needs to be modeled in the signature. For example, the SSL read and the SSL write APIs, which adds the line 8 on the left, are two main APIs used for developer to send and receive data over SSL channel. So these two APIs should be called only after the successful certificate validation. As a result, in this example, we also need to track this control flow from the two if condition to the SSL read and SSL write, as you can see the dotted arrow in this flow graph. In our solution, We use program dependency graph as code representation as well as signature representation. In this way, we successfully capture both the control flow and the data flow in our signature. And here, we show our signature for the open SSL APIs, and which is very similar to the flowchart as shown in the last page. And you may already notice that there were two parts in this signature. And that's because the OpenSSL has two correct API usage when validating the certificate. The one is already shown in our motivating example as check after the handshake, and the other is the checking during the handshake, which I will not go into the details because of the limited time here. And so we model the correct API usage for both cases, and if neither of the two parts is matched, a warning will be triggered in our system. Our SSLINT implementation has the following technical challenges. The first one is, given an SSL library, we need to understand the precise conditions for the correct usage and then model them in our signature. The second one is, given a signature, we need to identify preliminary conditions to decide if a signature must match. For example, in our open SSL signature shown in the last page, the data flow from the SSL new API to the SSL read or write API must be captured before the PDG-based signature is matched. So the last one, from an OS distribution, we need to identify that the select candidate apps using SSL libraries and successfully compile these apps for our analysis. In our implementation, SSLINT acts as a certificate validation, a vulnerability scanner. We use code server with a static analyzer provided by Grammatech for static analysis and generating PDGs. And SSLINT is implemented in C++, and it is about 2,600 lines of code. And our signature expression design is motivated from Cypher, a graph query language used in popular graph database Neo4j. And we also designed a custom algorithm to perform this signature matching. In our evaluation, we investigated apps leveraging on the most popular two SSL libraries on C and C++ platform. One is OpenSSL and the other is GluTLS. We designed signatures for both libraries, automatically scan over 22 million lines of code, and detect 27 previous unknown vulnerable apps out of 485 Ubuntu Linux apps. We have reported all of our findings to developers or maintainers and got 14 confirmations from developers, and so far 4 have been already fixed. Our result shows that the vulnerable apps from the various categories, as you can see here, we have email apps, we have web apps, and even database apps, and tools for administration and performance testing. And these vulnerabilities can lead to serious consequences such as privacy leakage and privilege escalation, and may cause great trouble for users. And here the table are our measurement result in detail. As you can see, the size of each code for each vulnerable app is between a few thousand lines to more than 100,000 lines. 14 of the vulnerabilities are either confirmed or fixed by developers. For those we have not heard from the maintainers or developers, we successfully launched the man-in-the-middle attacks on all of them. So we confirmed that they are really vulnerable. We refer to this part of the job as dynamic auditing, as listed in this table. Another interesting finding we found in our evaluation is that Ubuntu developers are only responsible for maintaining a small number of apps in its software repository. The other apps are maintained by the community. In our evaluation, we found that both the Linux distributions and the community Linux distribution maintainers and the community developers feel no obligation to fix bugs or vulnerabilities in Linux distributions. So we even found that examples which has already been got fixed in the community upstreams, but is still vulnerable in the latest Linux distributions. And it is also true for the other Linux distributions besides Ubuntu. We think such security problem in the open source software must be solved properly to avoid more vulnerabilities in the future. To conclude our work, we start from the motivating examples that there are a lot of misuse of the SSL APIs in application, and the design and implemented SSLINT, a system to verify the SSL API usage in a large scale. And we discovered 27 previous unknown vulnerable apps in the Ubuntu software, and most of which are also shared in other Linux distributions. And SSLINT is our first step to verify API usage by state analysis, but we believe that this approach is not restricted in SSL. So currently we are focusing on the following ongoing works. And the first one, we are building generic system to verify API usage in application of different programs, languages, such as Java apps. And the second one, we are trying to fix those failed applications in our analysis due to the memory explosions and the other errors by automatically identifying SSL relevant code in the application and only focus on that part of the code to reduce the workload of our static analysis. So in the end, I'd like to show you a tech demo video against one of the vulnerable email app we found. And meanwhile, I'd like to take your questions. And that's the end of my presentation today. Thank you. Thank you. So I may. Oops, sorry.
Hello, Cami Vanier, Indiana University. I'm curious how much of the signatures you were able to create just from the documentation, and how many of them you then had to later create based on looking at the examples you were finding. So were you able to actually just figure out what the correct one was up front, or how much did you have to go back and create new signatures after looking at the examples?
Okay, so my understanding of the question is how many signatures do we made? And yes, we made the signatures for GNU TLS. We have actually we have two, and we have OpenSSL. Actually, we have that one, and all of them are from the examples. Some of them are from the document, but as you know, the OpenSSL is poorly documented. So many of them are from the examples from the developers. Yes.
Thank you.
Oh, sorry for the video. 100 seconds. Okay.
So I'm Mike from the United States Military Academy. I just wondered if you had synthesized any lessons based on looking at the APIs and looking at your results, that you could kind of make some recommendations on how these APIs could be better. I mean, I know Georgiev and Fall and others have shown that they're bad, but anything like opinions on that you'd like to share? Okay,
so you asked me for opinions or, okay. First, we recommended all of the developers not to use OpenSSL. That's true. That's really poor design and poor documented. That's true. And I noticed that many of the vendors have already started their own projects on that libraries. So something like the Libre SSL or other libraries. And I think for now, many developers has known this fact that the OpenSSL is not safe. So that's a good thing, I think. Yeah. Thank you very much.
Okay. One other question I had, did you have any false positives when you were running through all these applications?
False positive, of course. As you know, I prepared for slides, but this video is now over. So, okay, false positive, of course, because developers can do some customizations to the OpenSSL libraries. So in that case, they can write callback functions inside the OpenSSL. So in that way, we cannot capture this for static analysis, but I'm pretty sure that we can do that in dynamic analysis, as we have some previous work has already done that.
Okay.
Yeah.
Cool. All right, let's thank Bojan and all the other speakers in the session.
Yes, thank you all.